Hello, everyone. In this video, we're going to go over section 1.3 of our notes on the derivative at a point on a curve. To get started on this idea of the derivative at a point, let's work up to it by first talking about secant lines on a curve or a graph. A secant line between 2 points, PQ, is a curve or a straight line between points P and Q on our graph. So I'll draw it here. So if we want to describe the slope of that secant line, well, we'd write the following formula. Let's recall that the slope of a line is equal to the rise over the run of that line. More specifically, the change in the vertical direction over the change in the horizontal direction between 2 points. So if our points here are P and Q, given with the coordinates A and F of A for P and A plus H down here on the horizontal direction and F of A plus H as the output, then the slope between those 2 points is going to be the change in the Y coordinate divided by the change in the X coordinate. So let's write that here. So that slope is going to be F of A plus H minus F of A all over A plus H minus A. Now we can look at the denominator here and see that the minus A cancels out with the initial A. So we're just left with, in the denominator, H. We can see that H represented on our graph as the distance between A and A plus H. So that H amount is the length of the distance between A and A plus H. So now I'm going to clean this up a bit and ask us to think about what happens as H, or that distance between A and A plus H, as it shrinks, as it gets smaller and smaller. As that happens, our secant lines going through P and whatever corresponding point start to center around one line in particular. I'm going to draw on that line. So as this H gets smaller and smaller, that secant line approaches the tangent line of our curve at that point. And I'm going to write that in. This line is the tangent line of our curve at the point P. And we can fill in our notes here. As H goes to 0, the slope of that secant line approaches the slope of the tangent line. We can call that tangent line T to the curve F at the point X equals A. Now I'm using P to represent that point, but in coordinates, again, the X coordinate of that P point is A. So now let's look at the definition of the derivative. Well, we've sort of danced around it a little bit, but the derivative is the slope of that tangent line. And I'm going to write that out separate. So the derivative of F at X equals A, or when X equals A, is the slope of the tangent line at X equals A. So here I've drawn that tangent line, and the slope of this line is the derivative at that point. Notice we're focusing in on a particular point on our curve. All right, so now let's look at that definition a bit more formally and write out a formula for how we might compute it. So because the derivative is the slope of that tangent line, we saw that the slope of the secant lines is given by this formula up here. So the slope of those secant lines become the slope of the tangent line as h goes to 0. So how we would write that mathematically would be, well, with notation, we have f prime of a, that's the notation for the derivative of f at a. It's going to be equal to the limit as h goes to 0 of the slope f of a plus h minus f of a all over h. So here, what we've just written down is the formula for how we'd compute the slope of the tangent line. It's the limit as h goes to 0 of slopes of secant lines.